All right, welcome back. This will be our final video in today's lesson. What we want to do is apply the formula we found before, which is to find the sum, the infinite sum of a geometric series. That is, we add up not just a few of the terms, but all infinitely many terms, and see if we can actually get an answer. Okay, we'll be looking at two examples, 2410 and 2411. Let's get started. So, the thing to remember is for an infinite geometric series, I equal 1 to infinity of ai, the formula that we got was a1 times 1 over 1 minus r. So basically, if you know it's a geometric series and you can tell me the first term and the common ratio, then we can plug in and get that infinite sum in a very straightforward fashion. So, part A, let's take a look. The sum, j equal 1 to infinity, don't let it bother you that they're using a j instead of an I. That's just our index variable. As long as it matches the thing that's here on the index of our variable, that subscript there, then we're okay. Where aj is equal to 5 times 1/3 to the j minus 1. Okay. And here they're using j as well instead of n. Don't let that throw you. Just treat it like an n if you like, or treat it like a variable that's in the correct place. So from this, I can tell that the first term, a1, is equal to 5, because in our formulas for geometric series, they always appear here. And then our common ratio, r, is equal to 1/3. So these are the key pieces of information. With those, we can easily calculate the sum j equal 1 to infinity. This is adding up all infinitely many terms of this thing. And what is it equal to? Well, it's equal to a1, which is 5, times 1 over 1 minus 1/3. Which is, let me see, 5 times 1 over 1 minus 1/3. We need a common denominator, which is going to be 3. 3 over 3 minus 1 over 3. And that's 5 times 1 over, let's see, 3 minus 1 gives us 2/3. Now I'm going to take that 2/3, flip it up to the top, or move it to the top and flip it over. So this is equal to 5 times 3/2. Multiplying, if we multiply these together, the 3 multiplies by the 5, and we get 15 over 2. That's our answer for the sum of the first series is 15/2. Okay, part B. Once again, I encourage you to pause the video now, go ahead and work through the rest of the parts, and then come back and we'll do them together. So part B, this one is sum, n equal 1 to infinity of 3 times 0.71 to the n. Now, this is a geometric series. The first term is 3. The common ratio is 0.71. Oh, wait a minute. Beware. They tried to trick us here. This doesn't exactly fit the formula because it does not have a1 times r to the n minus 1. And you might ask, does that matter? And the answer is yes, it does. And we'll see why. So let's just cancel out that a1. In order to find the first term, we need to substitute the number 1, that's the first index we use, into this formula, and that will give us the first term. So a1 is equal to 3 times 0.71 to the power 1. Now, that 0.71 to the 1 is 0.71, and 3 times 0.71 is 2.13. So, just as an observation, they're trying to fool you here into just thinking this is a1 and this is r. The r is still correct, but the a1 is not, and the reason is that this is not set up with the r to the power n minus 1. If you don't see an n minus 1 here, you can't just assume that the thing is correct. However, the power, you can see as we increase n, each time we increase n by 1, we multiply by another 0.71. So figuring out the r is still correct. It's just that a1 is a little different. Here our a1 is 2.13. Okay, with this a1 and this r, we can go ahead and figure out this sum is equal to 2.13 times 1 over 1 minus 0.71. It's 2.13 over 1 minus 0.71 is 0.29. And I moved the 2.13, I multiplied it by the 1 and moved it to the top. And then we have two different ways that we can answer this. One of them is to convert it to a fraction by multiplying the top and bottom by 100. If we do that, we get 213 over 29. This is in some way the best answer because we didn't have to round anything off. If you wanted to do it in a calculator, you could do 2.13 divided by 0.29, and that is equal to approximately 7.3448. Now, of course, there's more decimals than that. It goes on, and it's the fact that we don't record all of those decimals that makes this only an approximation, whereas since this is a fraction, it's exact. We didn't round this off at all. This one we rounded off. So in some sense, the first answer is preferable. It's more precise, it's more accurate, but of course, sometimes we end up needing or wanting our answers in decimals. And if I didn't state otherwise how the answer should be given, I would accept either one of these. Okay, on to part C. So, for this one, let's grab a copy of it. The first question, I guess, is this a geometric series? 500 minus 100 plus 20 minus 4. And the question is, as we move from one term to the next, do we always multiply by the same thing? So 500 times what is negative 100? Well, 500 we have to divide by 5, so that's like multiplying by 1/5. And since it changes from positive to negative, we better multiply by negative 1/5. I'll zoom in on this and just make these notes in color so we can tell this one is times negative 1/5. That's what we multiplied by. What if we want to get from negative 100 to 20? Well, once again, we're dividing by 5. 100 divided by 5 is 20, and it's changing from negative to positive. So once again, we're multiplying by negative 1/5. In the third case, if we multiply 20 times negative 1/5, we do indeed get negative 4. And so this confirms that this is a geometric series, and the R is equal to negative 4. So the R is equal to negative 1/5. That was crazy talk. Okay, and then A1, our initial term, is 500. Now, question, is R between minus 1 and 1? Because you can only add up a series if the ratio is between negative 1 and 1. Here R is a negative number, but it's negative 1/5. That's negative 0.2, and that is indeed between minus 1 and 1, which means that we are allowed to use this formula. Yes, we can use the formula. So let's go ahead and plug in. This sum, the sum will be equal to A1, which is 500, times 1 over 1 minus 1/5. Be careful, there's a negative on the bottom because it is 1 minus R, and R itself is a negative number. So we get those two negative signs down there. This is what our sum is equal to. This is the sum, I equal 1 to infinity of AI, is equal to 500 times 1 over 1 minus 1/5, which is 500 times 1 over 1 plus 1/5. That's 500 times, on the top we have 1 on the bottom, we get a common denominator. The 1 becomes 5 over 5 plus 1 over 5, which is 6 over 5. And then we flip that 6 over 5 up to the top and make it 5 over 6 and multiply. So 500 times 5 over 6. I guess we also multiply by the 1 that was on the top of that fraction, but that just that doesn't change anything, that disappears. So 500 times 5 over 6, which is 500 times 5 is 2500 over 6. And you have a choice. You can give it either as a decimal, which will involve rounding off, or we can simplify that fraction. Here, 6 does not go into 2500 evenly, but we can cancel 2 out of the top and bottom, and we get, on the bottom, if we cancel a 2, we get a 3. And on the top, we get 1250 over 3. I'm going to leave that answer as a fraction. That's exact. If you wanted to give a decimal approximation, you could divide in a calculator 1250 divided by 3 and then write down as many decimals of that as you wished. Okay. That's our answer to part C. Let's take a look at part D. Okay. So let's grab a copy here. Okay, for this one, well, is it a geometric series? Do we always multiply by the same thing to get from one term to another? It looks like to get from 3 to 6, we would multiply times 2. To get from 6 to 12, we would multiply times 2. To get from 12 to 24, we would multiply times 2. From 24 to 48, times 2, etc. It looks like it is a geometric series. So this is a geometric series. R is equal to 2. Our first term, A1, is equal to 3. However, if we want to use the formula, we need to know that R lies between -1 and 1. And here R is equal to 2. It does not lie between -1 and 1. R is not between -1 and 1. That means we can't apply the formula. Can't use the formula. However, I can make the following observation. These numbers are all positive, and they keep getting bigger, and we're adding all of them together, which means that somehow, when you get to the end, the answer is going to be infinity. It's less clear if they alternated between positive and negative, because then things would cancel out. It wouldn't be totally obvious what was going on there. But in this one, it just gets bigger and bigger and bigger. It's equal to infinity. If we don't treat infinity as a number, then we wouldn't say that this has an answer equal to a number. But saying that it equals infinity does give us some information about what it does. It says it keeps getting bigger. If you said we cannot add these up or there is no answer, I would accept that as well. Okay, that is the end of part D. We are going to look at one more example. We've finished this example. We're now going to look at 24.11, and then that'll be it for today. Now, 24.11 is interesting. It's a little bit different. It asks us to look at a decimal number, a repeating decimal, 0.555555 ... What this is going to do is it's not going to be a simple find the sum of a series exercise. Instead, we're going to try to use these ideas to understand something about repeating decimal numbers. Okay. The instructions say, consider this number, rewrite this number as an infinite geometric series. And if you have a repeating decimal, this can always be done. The way that we do it is we do it digit by digit. So what I want to do is the things I'm going to add together are 0.5, that takes care of the first digit, and then 0.05, that takes care of the second digit. If we add these together, we get 0.55. And then 0.005, and then 0.0005, and then 0.00005, and etc. And if we add all of these up, we get this decimal number, 0.55555, repeating to infinity. Okay, so that number, 0.55555, is equal to this, and this is now written as a sum. Question, is it a geometric sum? Well, let's look at the terms and think about what do we have to multiply by to get from each term to the next. So to take the term, the first term, 0.5, and we want to get 0.05, you can see that we just have to shift the decimal over, and this can be done by dividing by 10 or by multiplying by 1/10. So to get from there to there, we multiply by 1/10. Similarly, from 0.05 to 0.005, we multiply by 1/10. And from 0.005 to get to 0.0005, we multiply by 1/10, etc. Now, that shows this is a geometric series. So the answer to this is yes, and in addition, we found the common ratio. The common ratio is 1/10. The other observation that we need to make in a geometric series is what is the first term? The first term is 0.5. Question, is R between -1 and 1? And the answer is yes, 1/10 is between -1 and 1. So -1 is less than R is less than 1. That's like a check, and that means we can use our formula. So now let us see what happens when we rewrite this using our formula. Okay, so this number, 0.55555 ... is equal to, well, it's a sum, I equal 1 to infinity of these AI, where the AI are geometric, and they have a first term 0.5 and a common ratio 1/10, and we know how to add up the sum of a series. We know what this is equal to. It may not be obvious what the answer is going to give us. The answer is just going to give us something that this number is equal to, and sort of who cares? The reason we care is that this is going to convert this decimal into a fraction. It's going to tell us what fraction this is equal to. To me, this is like magic. So 0.5 times 1 over 1 minus 1/10. Now, I want to do the following things. The 0.5 in the front, I know that 0.5 is the same as a half, so I'm just going to replace that 0.5 with a half. And then here, I'm going to get this fraction. The top of the fraction is just 1. The bottom of the fraction, we need a common denominator. That's 10 over 10 minus 1 over 10. We still have a half out in front. This is equal to 1 over, let's see, we have a common denominator, 10 on the bottom, and we have 10 minus 1 on the top, which is 9. So now we take that 9/10 on the bottom of this big fraction, we bring it to the top and take the reciprocal, we flip it over, and we still have that 1/2 in front. So this is 1/2 times 10 over 9. What is this thing equal to? It is equal to, well, we can cancel a 2 out of the bottom and top, and it's left with 5 on the top and 9 on the bottom. So what this says is that this repeating decimal, 0.5555555, is actually equal to a fraction, and the fraction is 5/9. Now, that's amazing because it's allowed us, using this formula and thinking of this as a geometric series, has allowed us to convert from a decimal back into a fraction. Now, you can go the other way. If you take your calculator and go 5 divided by 9, it will tell you this. But going the other way is not so obvious how you would convert this into a decimal. That's it. That's the end of this problem. Can you figure out what fraction it is equal to? Yes, and as you know or may remember, anytime you have a repeating decimal, or whether it's a single digit that repeats or a series of 2 or 3 digits that repeat over and over again, those always correspond to fractions, but it's not always obvious what fraction they correspond to. I'm going to give you guys one more challenge problem, and I'm not going to work through the answer, but I encourage you to try and work it out using reasoning similar to the above. Here is your challenge problem. What fraction is the number 0.1313131313 ... equal to? So this is a repeating decimal. It repeats every 2 digits, 13, 13, 13, 13. And my challenge to you is try to figure out what that is equal to. That's the end of our lesson for today. Take a look at the web work, see if you can figure it out, and let your instructor know if you have trouble.